Are you getting enough sleep? Well, that's the thing that we're going to try to answer. On today's Stats Medic, we're going to be looking at the average and we're going to make an hypothesis test based on an average. So let's go ahead and get started and we'll see what we got. Well, it's recommended that teenagers get 8 hours of sleep a night. Mr. Ferreira believes that his AP Stats students are getting less than the recommended 8 hours of sleep per night. To test his belief, take a random sample of 10 students in this class and record the number of hours of sleep in each one. Do these data provide convincing evidence that AP Stats students get less than 8 hours of sleep? Using an alpha level of 0.05. Number 1 says to calculate a sample mean and a standard deviation, and we can't really do that right now, of course, because we're doing this online, but I can tell you what my last class got. Last time we did this, we got a X bar of 7.1 and a sigma X of 2.9 hours. And remember that that is a sample of 10 students. Okay, for question 2, we're supposed to state appropriate hypotheses for the significance test, and then to define the parameter. Since we're talking about a mean, an average, the parameter that we use is going to be mu. So mu is the true mean hours of sleep per night for AP Stats. For the hypotheses, we're looking at H naught of mu equals 8, and alternatively, mu is less than 8. And where does that 8 come from? The idea here is that you can't use 7.1 because 7.1 comes from the sample. What we want to do is we want to figure out what is the true mean amount of sleep. And based on the reading, I see in the first sentence that we have a recommended 8 hours of sleep. And then on the second sentence, I see that we believe we're getting less than 8 hours of sleep. So that tells me that my null value is going to be 8. This means that if my null value is 8, my null hypothesis is mu equals 8, and my alternative hypothesis, mu less than 8. Remember, your sample data does not go into the parameter because it is from a sample, not from the population. It is a statistic, not a parameter. Number 3 is the conditions and what conditions need to be met. Same 3 conditions from last time: random, 10%, and normal. Let's go down the list. First with random. And we have a random sample of 10 students. Again, I like to quote a part of the problem so that these results don't seem to come out of nowhere. For 10%, our sample size is 10, and if we multiply that by 10, we get 100. So as long as there are more than 100 AP Stats students, then this is a valid 10% condition, or we have satisfied the 10% condition. So since there are more than 100 AP Stats students, n is less than 0.1 times n. Moving to normal. There are 3 different ways to satisfy the normal condition, and we'll go through all of them. The first thing you want to do is check if the population is normal. And of course, we have no indication based on our reading that the population or of everybody's AP Stat student sleeping time, we have no indication that that is a normal distribution. So we can't use that. The next thing that we want to check is to see if the sample is large. And if the sample is large, meaning greater than 30, then we have satisfied the normal condition. However, the sample size is only 10, so we can't use the sample size as large, the central limit theorem, to satisfy normality. This leads us to the third way to check normality, and that is a sample with no strong skew or outliers. Just to review, if your sample has no strong skew or outliers, then that is an indication that your population is normal. And if your population is normal, then your sampling distribution will also be normal. So let's take a look at the dot plot of our sample. Here's a dot plot for the amount of sleep in our sample of 10 students, and we can see that there is a peak over here at 8. There's a mound shape at 8, and there is a pretty low observation that's somewhere less than 4 hours of sleep. Poor guy or girl. But you know what? That doesn't look like a strong skew. I say that there is skew there, but it is not a strong skew. And I don't think that that's far enough for us to consider that an outlier as well. So you are probably going to be okay to use normal procedures here. Now, the word that they would like to use for this is that the T procedures and normal procedures are quote unquote robust. So robust means that even if we don't have a perfectly symmetric distribution, even if we do not have, perfect mound shape, we're still okay to use the T distribution, even though things are not perfect. That's what we mean by a robust procedure. It can take a little bit of abuse, I guess, is what I'm saying. When we copy that over to our worksheet, we can, definitely no strong skew, no outliers. So we are okay to proceed with this hypothesis test. Remember, a little bit of skew is okay. Skew is fine because the T procedure is quote unquote robust. The advice here also is if you are looking at a smaller sample, or if your population isn't normal, if you are using this no strong skew or outliers, then you really should be drawing a quick dot plot. It doesn't have to be the most exacting thing. I kind of fear whenever I say that because, I don't want to see really bad dot plots, but you don't have to make the most detailed dot plot. So that said, let's go on to number 4, which is give the formulas for the mean and standard deviation for a sampling distribution of x bar. Mu of x bar is just mu, which is 8.0, which brings up the other thing that is you want to use the values from h naught because you are assuming that h naught is true. So if you're assuming h naught is true, you're assuming that mu is equal to 8.0, which means you are assuming that mu of x bar is 8.0. Now for sigma x bar, we're going to take a slightly different approach. We know that sigma x bar is exactly equal to sigma over root n. But the problem is we don't have a value for sigma, so we have to approximate this. We're going to approximate this with s over square root n, which reminds me that I put the wrong notation here. That should have been sx and not sigma x. My mistake. So s over square root of n. This is 2.9 over root 10, or 0.92. Notice that I went one more decimal place than mu. I have mu at 1 decimal place, so my sigma is going to go to 2 decimal places. And again, we're using s to approximate sigma. Next task is to draw a picture and calculate the test statistic. Starting with the test statistic, we know that the test statistic is the statistic minus the null over the standard error. Specifically for this, we have a t is equal to x bar minus mu over s over square root n. We already calculated the standard error to be 0.92, so we'll just substitute that in for s minus s over root n. That gives us a test statistic t equals negative 0.978. We've got our nice normal curve that we always use. Zooming into our picture, we can see that we've got a really nice normal curve here. The bottom of the curve is labeled normal distribution 8 and 0.92, which is the mean and standard deviation. We've labeled the mu of the curve at 8.0. That's the mean of the sampling distribution. We've located where 7.1 is, and we corresponded it with negative 0.978 on the normal side of the curve, which has a mean of 0 and a standard deviation of 1. So that is a really nice looking curve. That's about as much as you're going to need here. And just looking at the area, that area looks pretty big. Looks like a lot of area, which means our p-value is probably going to be a large value. Remember, since we're working with means, the test statistic is a t-value, so we're supposed to use table B to find the p-value. And actually, we're always going to be using our calculator. So let's grab a calculator here to figure out the p-value, since we haven't done that as much. From the home screen of your calculator, you're going to hit second vars for the distribution menu. We're going to go to TCDF, number 6, and we're going to put in our lower and our upper. So our lower value is negative 1e99, which is basically negative infinity as far as the calculator is concerned. The upper is going to be our test statistic, which I believe was negative 0.978. And then we go to degree of freedom, and that is a sample size 10 minus 1. And then we paste that. This gives me a p-value of 1768. Over on your paper, you're writing the p-value is the probability that t is less than negative 0.978. Optionally, you can write TCDF, low is negative infinity, high is negative 0.978. DF is 9. That gives us 0.1768. And for good measure, we're going to write down DF equals 9, because I'm not sure if you're going to be writing that TCDF notation, but make sure you're writing DF equals 9 somewhere on your paper. Finally, what conclusion can we make? And I think you know what to do at this point. Copy and paste from the list of sentence frames, and then choose the correct path. We're choosing greater than alpha because remember that alpha was 0.05 and 0.17 is bigger than 0.05. Large values of p do not support the alternative hypothesis. So it does not support that the true mean hours of sleep is less than 8.0. Remember, the true mean hours of sleep, that comes from the state part, although we didn't write state. You know that that's a state part right here. True mean hours of sleep for AP Stats students. And less than 8.0, that is our alternative hypothesis where we had mu less than 8.0. Read it one more time just to make sure it's readable, and I think we're okay here. So that is a good summary. Now, I want to remind you that even though we concluded that the data didn't support that the true mean hours of sleep is less than 8.0, that doesn't mean necessarily that the true amount of sleep isn't less than 8.0. It means that with the data we have, with the sample that we took, we were unable to distinguish whether or not what the true mean hours of sleep was less than 8.0. So we weren't able to make that distinction because of sampling variability. The small sample has a large amount of sampling variability. So 7.1 hours was not sufficiently different than 8.0 to make us say conclusively, or at least at the 5% level, that the mean hours of sleep is less than 8.0. So we're not saying that it's not less than 8.0. We're saying that we didn't detect, or we couldn't tell based on the data, that the mean hours of sleep was less than 8. That's a very slight difference between those two statements. So let's go on to our important ideas. We've got the conditions for a significance test of mu. Those conditions are a random sample or random assignment of treatments. We have the 10% condition and the normal condition. Remember, the normal condition means that we either have a normal population, or we have a large sample greater than 30, or we have no strong skew or outliers. If you use that third statement, no strong skew or outliers, you need to either draw a dot plot or a histogram of your data. Learning target 2. The test statistic is the t x bar minus mu over sx over square root of n. Catching a couple last minute typos here. And then the third thing is our p-value. Our p-value is a probability that the t-score is less than, well, maybe not just less than. So greater than, less than, not equal to, and we have the TCDF. You have to write low, high, DF. There's no way to use the data. You have to use the t-score. And that's what the note says. You have to use t. And don't forget to use your degree of freedom, or to write your degree of freedom somewhere. Okay, this brings us to check your understanding. The level of dissolved oxygen, DO, in a stream or river is an important indicator of the water's ability to support aquatic life. Love that aquatic life. A researcher measures a DO level at 30 randomly chosen locations along the stream. And here are the results in milligrams per liter. X bar is 4.77 and SX equals 0.939. An average dissolved oxygen level below 5 puts the aquatic life at risk. So do the data provide convincing evidence at the 0.05 significance level that the aquatic life is at risk? So I love this question. I mean, aquatic life, dissolved oxygen is everything I want in my world, right? Those of you who know me, you know what I'm talking about. So what do we got? We got the parameter. The parameter is mu is the true mean DO level in the stream. Hypotheses, let's remember that 4.77, that is a X bar, so that is not our null value. And our null value should be this 5.0, because that's where we want to test things. We want to test things and see if the mean level is below 5.0. Okay, so H naught mu is equal to 5. H alternative mu is less than 5. Our statistic is highlighted, or I highlighted it earlier. We have X bar is 4.77. For the alpha level, that's also given, and that's alpha is 0.05. Name of the procedure, same idea. This is just one sample. The correct curve we're going to use is a t-curve. So it's a t-test, and the parameter is a mean. So t-test for a mean. The next thing is to check conditions, and it's the same 3 conditions. We've got random. We have random 10% and normal. The problem itself says 30 randomly chosen locations. So we'll quote that and use that as justification for random. For the 10% condition, there are likely more than 30 locations in that, or 300 locations in that stream. Remember that 300 comes from 10 times the sample size. 10 times 30 is 300. So if that's true, then n is less than 0.1 times the population. And let's go through this sample size, or the normal conditions. The first normal condition is a normal population, and of course nothing in the problem says normal population or normal anything really, so we can't use normal population. The next thing we want to check is a large sample. So is n greater than or equal to 30? And yeah, it is. My sample size is 30, and that's greater than or equal to 30. So I'll put central limit theorem at the end here, and we have done it. We didn't have to make a dot plot. Great. So we've just checked the conditions. So we are on the do phase. Let's do some stuff. The general test statistic is statistic minus null over standard error. The specific formula, t is equal to x bar minus mu over s over square root of n. Now, previously when we were learning this, I made a big stink about approximating sigma with s. And here we're just going to do it, we've learned it, so we're not going to, again, make a big stink about it. For the work, just go ahead and substitute all of those numbers in there. 4.77 minus 5.0 over 939 over root 30. For our picture, I think what I'm going to do is I'm going to do this over on the side. Ooh, that's a lot over on the side. Pardon me. Okay, so this is good over here. Let's go ahead and put our normal curve. Over on the bottom, we're going to label this with the mean and standard deviation of our sampling distribution. So the bottom numbers are going to be from a normal distribution of 5 and 0.17. Next, you're going to label your mean and your x bar. Now, to figure out where you're going to put that 4.77, you're probably going to have to compute the test statistic. So let's do that now. If you calculate that t over here, you're going to get negative 1.342, which gives you a place to put your 4.77 somewhere around 1.3 looking up here. Now your x bar and your test statistic really always should be vertically opposed from each other, right on top of each other. We can estimate where 1.342 is, negative 1.342, and then we're going to shade. Now our alternative hypothesis, if we remember, is that mu is less than 0.5, so we are going to shade to the left. So looking at what we've shaded over here, this looks like a pretty sizable p-value. So, we're going to expect that. That's going to give us a way to make sure that our calculations are what they expect them to be. We're going to expect a pretty large p-value here. Let's pop that drawing right back into our worksheet and we'll continue things. We already have our test statistic, so let's go ahead and write that down again. Our test statistic t equals negative 1.342. Now the p-value is equal to the probability that t is less than negative 1.342. That's the same thing as the TCDF, where the low is negative infinity, the high value is negative 1.342, and our degree of freedom is 29. That gives us the value 0.095. Of course, there really is a 0 at the end here, but you do not have to write it. Also, I put a DF equals 29. If you're not writing the calculator notation on your paper, and you don't have to, of course, but if you don't write that, make sure that you write on your paper somewhere that you know the DF is equal to 29. And then we're going to conclude. Go ahead and copy and paste the sentence frame for a conclusion. Since the p-value is, that's greater than our alpha, isn't it? Greater than alpha means we do not support the alternative hypothesis. I should have said the data doesn't support the alternative hypothesis. Maybe us as people, maybe we actually do support the alternative hypothesis, but that doesn't matter. What matters is, what does the data say to us? So the data does not support that. Well, what was mu again? Mu was the true mean DO level in the stream. So it doesn't support that the true mean DO level in the stream is less than 5 milligrams per liter. And that was pretty readable to me. So that does it for our significance test for a mean. That was, a fair amount of work that you're going to have to do for this. And so that said, we'll see you next time.